Il y en a en ligne. J'ai compris. J'ai compris.
Bon, bah bonjour. J'espérais réveiller un peu, mais non. Je vous remercie d'être là. Aujourd'hui, on a voulu faire ce qu'on pourrait qualifier de séminaire d'ouverture sur un sujet qui semble concerner quand même pas mal de monde, sur les questions nucléaires. Donc moi, c'était quelque chose qui m'intéressait, que j'avais envie de voir. Beaucoup le savent pas, mais c'est ma formation initiale, c'était de faire de la physique nucléaire. Heureusement, j'ai un peu changé. Et puis ici, on fait quand même un petit peu de physique nucléaire aussi, du moins dans des environnements cosmiques. Donc, c'est pas exactement les mêmes principes. Et puis, j'ai vu il y a quelques années un exposé de Sylvain qui mélangeait clarté d'esprit et d'exposition avec faits scientifiques sérieux et avérés. Et ça, c'est intéressant parce que sur ce genre de thématique, on entend beaucoup d'opinions très, comment dirais-je, très affirmées et dont la légitimité ou le contenu informatif peut être certaines fois discutable, pour le moins. Voilà, donc moi, je voulais en savoir un peu plus. Alors, je précise que ce n'est pas depuis le 1er janvier que j'ai demandé que Sylvain vienne. C'est depuis quelques années déjà que j'avais demandé ça. Quant à Sylvain, lui, il est directeur de recherche à l'IGCILAB, délégué scientifique à l'IN2P3 pour l'énergie nucléaire. Donc, autrement dit, je pense qu'on peut lui accorder une assez bonne légitimité dans la thématique qu'il va nous exposer. Et donc, il est maintenant très spécialisé sur pas mal de sujets liés à l'énergie nucléaire dont il va nous parler. Et donc, je vais lui laisser la parole. En fait, c'est plus simple. Merci.
Merci. So, good morning. I will make the presentation in English. So please be indulgent with my beautiful English. Thank you very much for the invitation. I have proposed to speak about nuclear energy for the future, from the very basic point of view of the physics of the reactors and of the physics of the fuel cycle. And I try to show you how we could, for example, make reactors that reduce a lot the consumption of natural uranium based on very basic physics. And I try also to show how the decision we are making today have big consequences for the future and our capability to deploy such generation 4 reactors. So I will talk a lot about the plutonium. Okay, so first the warnings, the law of the physics do not change. So I don't show very new things about nuclear energy. It's always the same: fission, neutrons, breeding, and so on. And I just want to start with only one slide on the energy context or energy problem or climate energy problem to show. I have represented here the trajectories of different countries in terms of carbon emission on the y-axis and energy consumption on the x-axis. It is per capita. Okay, and you see, you see the evolution of the trajectory of the country between, let's say, 1980 and present day. So you have USA here, Germany, France, and Sweden, for example, and China is here. And the line represents simply the mass of carbon emitted per unit of energy by fossil fuel, gas, petrol, coal, coke, and oil. Sorry. So what we can see is that the main rich countries or present rich countries are reducing the emission of carbon dioxide per capita, USA, Germany, and so on, but remains completely in the field of between the gas and the oil, and they reduce the emission mainly by the reduction of the energy consumption per capita. And it lasts during, since 20 or 30 years. You see here China and India, which are exactly on the gas line, and the carbon emission are increasing linearly on this line. And we have two special cases, France, which went out of this fossil area by developing the nuclear power in the 70s. And you see that the energy has increased and the carbon emission remained constant during 20 or 30 years. And now we are reducing the carbon emission mainly by reducing the energy consumption per capita. You see also here in the black line, is the quantity of carbon emission we have to reach in 2050, 60, 70, I don't know, but to limit the evolution of the global temperature on Earth. So it is around 1.5 tons of carbon, of dioxide carbon per capita and per year. So you see all the challenge to reach for each country this line. And we have two ways to reach it by reducing the consumption. It means displacing the dots on this line and find a very low consumption of energy, which is much less that we can see in Asia, for example, today, or to, of course, develop energy sources which do not emit carbon. Okay. So you already know this big challenge. Yes.
You read on the news always the Chinese are making lots of nuclear reactors, but they're increasing their output in...
It's not a lot. The Chinese dimension, I would say, it's perhaps between 5 and 10 per year. So yes. Yes. The evolution of the energy in China is mainly on coal today and gas. And even if it is a lot of nuclear reactor, it doesn't play a major role today. Only one slide also to warn you about how do we quantify the energy in France. Perhaps you remember the debate in 2007 between Ségolène and Nicolas. And we had 5 minutes of discussion during the presidential election. 5 minutes about how much nuclear in France. And Ségolène said 17%. Nicolas Sarkozy said 50%. So I just want to warn you about the difficulty to quantify the energy and to discuss about energy and to make to discuss about energy in a quantitative way. So you see here a very simple energy mix in France. Very, very simplified, simplest energy, 100 joule for heating, 100 for gasoline and for transportation, and 100 for nuclear energy, for example, and for electricity. You know that when we transform heat into work, into electricity, we have thermal efficiency, about 33% in the nuclear reactors. So the physical energy we use is the thermal after the thermal efficiency, mechanic for the transportation, and electricity for the electricity. So if I look at the part of nuclear power of the very simplified mix, it's 33% if I take the primary energy and only 23% if I take the final physics energy. But you have to know, you probably know that we quantify also the energy with the convention or with the final energy. And the definition of final energy is the energy which is bought, acheté, purchased by the final consumer, final user. And you saw the bias which we have here. We bought the gas before using it. We buy the oil before using it in the car. So before the transformation from thermal to mechanical, and we buy the electricity after the transformation. And this is the real definition of the final energy, which is a big issue for me from the physics point of view, because we mix different kind of energy, and we should not be allowed to some or to discuss about this. But the quantity of nuclear energy in this case is only 24%. So what I want to say is that if you want to show that we can stop nuclear power in France, you choose the red one. And if we want to show that it is not possible, you choose the blue one. So you have always a bias in the discussion about the way that we have to count the energy. So please be careful with that. Okay, nuclear energy in the world, you know that the production is relatively constant in the world. It's about 2,700 terawatt-hour per year. It's perhaps 10% of the electricity in the world, 3–4% of the global energy in the world. So it's very low. The projects or the reactor in construction today are mainly in Asia. I said in China, it's a bit perhaps 5 reactors per year which are constructed. The market is very calm in Europe. You can see the EPR project, which is the main French reactor, which is built today. 2 reactors in operation in China, 1 in Finland. Flamanville, you will see that it should start this year, maybe. And we have announced 6+8 APR in the coming 10–15 years. So it's a relatively calm market, I would say. For the future, it can be relatively different if we take into account the climate constraints. You see here some different projection which has been made in the 2012 by different international organizations working on energy perspective. We are here today, 2020, 2050 is here, and the minimum of nuclear power in 2020 is a stable production at the world level, and the maximum is around a factor 10 as compared as today. So maybe it's not possible to reach a factor 10 in 2050, but it can happen in 2060, 70. I don't know. So I will talk about the sustainability of the nuclear reactors, the uranium resource, and so on. So we have to make some hypotheses about the nuclear demand in the future. So I will take factor 1 at the low hypothesis, and factor 10, the big, the large hypothesis for nuclear demand, and we discuss the capacity of producing this kind of energy based on nuclear resource. Only fission. There is no fusion energy in the global perspective, as far as I know. Yes, it's a very big process. It's very long, but I don't think there is fusion here. Okay, I show a very simplified scenario we have made ourselves about energy mix at the world level, which fulfill different constraints. The first is the world energy demand on 20 billions of ton oil equivalent per year. It's around the factor 2 as compared as the year 2000. Climate constraint, the division by 2 of the carbon emission, a large renewable production, about 7.5 billions of ton oil equivalent, a large storage of carbon, which is perhaps completely unrealistic. And the result of this very simplified scenario is that we have to multiply by 8 the nuclear power. Nuclear power here is mainly dedicated to electricity production for very concentrated population, I mean urban population, in the world region that already have the technology of nuclear reactor. I just want to show you the results here. You can see the red line. You see factor 8 is a very, let's say, aggressive scenario for nuclear deployment. I completely agree, but you see that in Asia, for example, this factor 8 at the world level correspond at around 2,000 kilowatt hour per year per capita. 4,000 in the present rich countries. I show you the French case today. We are at 7,000 kilowatt hour per capita per year. So I just want to say that the factor 8 at the world level is much, much less. That's the French case that has been made in 15 or 20 years during the 70s. So perhaps we can, okay, so it's not so unrealistic when we see the economic dynamics in Asia, for example, to reach this kind of nuclear demand in the future. J'ai commencé à quelle heure? Je sais pas. 5, okay. So, very basic things about nuclear energy. You know that we use heavy nuclei, mainly uranium, which are at the right part of the nuclei chart. We induce a fission on uranium that produce energy and neutrons. And the neutrons produce again a fission and can maintain like this a chain reaction and the power produced. So just some order of magnitude, the fission, the energy of the fission is around 200 MeV, millions of electron volts. The molar mass is 235 grams per mole. So we can already, with these two things, calculate that typical nuclear power, nuclear reactor, the power is around 1 electrical gigawatt. The thermal efficiency is 33%. So the thermal power is 3 thermal gigawatts, sorry. So you can calculate the number of the fission per year. It's energy divided by 200 MeV. It's this number of fission. So it means that the mass of fissioned material in the reactor per year is the number of fission divided by Avogadro, multiplied by the molar mass, and so on. It's 1 ton, around 1 ton. Okay, so this gives you an order of magnitude of the real consumption of material by a typical nuclear reactor per year. You know that in France, we have around 60 reactors for 60 million of people. It means that we use 1 gram of fission per capita and per year. I just want to show you this very simple calculation but you already know that. The nuclear reactor transforms mass into energy. And the mass we have lost in the reactor per year for always this 1 gigawatt reactor is simply the energy produced divided by C squared. So the lost mass is a very beautiful calculation. So the energy produced is 33 10 to the 9 watts. times the number of seconds per year, you know that it is pi 10 to the 7. This is second per year, divided by 3 10 to the 8 square. And it's very beautiful because this is divided and it makes 1. Okay, so the nuclear reactor transforms 1 kilogram each year into energy. So we see that the concentration of energy is very high because we have 1 ton of fission, and after that we have only 999 kilograms of fission fragments, and 1 kilogram has disappeared and became energy. Okay, so in the ground we have only 3 main heavy nuclei, you know that, uranium, 2 isotopes of uranium, uranium-4 is completely negligible, so uranium-5, 235, 238, I will say U5 and U8, and thorium-232. Unfortunately, the capacity of a nuclei to fission when he meets a neutron, and a low energy neutron, is completely different between U5 and U8. And uranium-5 has an odd number of neutrons, and this leads to a high capacity of fission by a neutron. So to simplify, we can say that uranium-5 is a fissile nucleus which can, and the neutron can induce fission on U5 and cannot on uranium-8. And unfortunately, the natural uranium contains less than 1% of uranium-5, so we dispose of not so much fissile element in the ground. Okay, so you also know that we have a chain reaction in the reactor. A fission emits around 2.5 neutrons, and at these 2.5 neutrons, we ask only that 1 neutron induces a new fission to provoke a new fission, to produce energy and to produce new neutrons and so on, and the chain reaction may maintain the power constant in the reactor. So I just want to say that this is really easy in terms of the neutron balance because we produce 2.5 neutrons and we need only 1 to maintain the chain reaction. So we have to manage 1.5 neutrons to be captured by other nuclei. So it is really easy, and we will say after that in some other cases it's not so much. Okay, so the neutrons must have a high probability of fissioning the material, but you have to remember that the concentration of the fissile nucleus in the uranium is very low, less than 1%. And if we look at the cross-section, the cross-section means the probability to induce such a reaction, fission or capture. Capture, it's a very simple reaction. The neutron is kept by the nucleus and the life of the neutron is over. So these probabilities are strongly dependent on the neutron energy. So we can see here in a very basic approach, which are the cross-section of fission in black for uranium-5 and capture in rose for uranium-8. We can see the story of the neutron and how we can make a nuclear reactor with a chain reaction. So fission are produced by the fission at high energy. High energy in the reactor physics is around 2 MeV, millions of electron volt. And at this energy, you see that we have a factor 10 between the probability to produce a fission on U5 or a capture on U8. But we have to remember that we have a ratio between U8 and U5 in natural uranium of more than 100. So when the neutron enters the uranium at this energy, the main reaction is the capture on uranium-8, and there is no possibility to have a chain reaction. You see that at low energy, I mean, it is a log scale, so below 1 electron volt, The difference between fission of U5 and capture of U8 is around 200 or 300. And here, even if we have a small concentration of U5, we can have a high probability of fission, even if we have more nuclei of uranium-8. So if we want to use the uranium natural uranium or low enriched uranium, low enriched mean a low concentration of uranium-235, let's say 3–4%, we must absolutely slow down the neutrons, and we have to slow down very efficiently to help the neutron to cross this very dangerous energy zone where we have a lot of resonance of uranium-8, and the neutron can be captured during the slowing down. Okay. So the nuclear reactor today use a neutron moderator, which is a water, because water contains hydrogen. Hydrogen is light, and a light nucleus is very efficient to slow down the neutrons. All the reactors in the world work like this. The neutrons are produced at high energy, the moderator slows down the neutrons, and the fission is produced at low energy of the neutrons. In France, we use pressurized water reactors. The fuel is enriched at around 4% of uranium-5. Okay, so you see the very basic principle of the reactor. The uranium enriched is here in the core. We produce thermal energy, and the rest of the reactor is made to transport the thermal energy to the turbine and to transform the thermal into mechanical and then into electricity. Okay, so this is the present PWR, pressurized water reactors. This is the EPR. It is exactly the same basic behavior. Enriched uranium, 4%, water to slow down the neutrons. Water also is used to transport the thermal energy to the turbine, and it is, again, exactly the same. Okay, from the point of view of the fuel cycle, so we use here the UOX fuel. UOX just means oxide of uranium oxide, 4% of uranium-235. It is produced by natural uranium. Natural uranium is enriched, and during the enrichment process, we produce depleted uranium, which contains still, let's say, 0.25% of uranium-235. This depleted uranium today is not used. Okay, the fuel remains 3–4 years in the reactor, and at the end, we have lost a few percent of the fuel. The 96% of the fuel did not react with the neutrons. It remains uranium-238, and in the 4%, we have produced plutonium, mainly by neutron capture on uranium-238. We have produced heavy nuclei as americium, curium, neptunium by cumulative neutron capture on uranium and plutonium. And of course, we have produced fission products, which is a result of the fission of uranium-235. And the number here are the very order of magnitude for the French case. So we produce, let's say, 10 tons of plutonium per year, 1 ton of minor actinides, and 50 tons of fission products. And on these 50 tons, only 10% are radioactive with a long period, around 5 tons per year. And this is, of course, the nuclear waste. Okay. So this is the cycle 0. I will speak about the multi-recycling after, but you must know, you already know that this very basic cycle, uranium enriched, 3 years in reactors, and the spent fuel is a cycle which is used in US, for example. There is absolutely no reprocessing of the spent fuel. So this spent fuel is American nuclear waste. It contains the plutonium, it contains all the nuclear which has been produced during the irradiation. In France, we reprocess the fuel, so we extract the material which can be used again in the reactor. We contain fissile material. It is the case for plutonium. So the plutonium is extracted, separated, and we produce a mixed oxide fuel, and is spent again 3 or 4 years in the reactor. We recover also the uranium, because the uranium contains still 1% of uranium-5, so it is a fissile element. We can re-enrich the spent uranium and produce a new UOX fuel and spend again 3 or 4 years in the reactor. So we did this in the past, and we start again this strategy of uranium recycling. In terms of power, the MOX in the French case, it's around 10% of the power in the French reactors. And if we recycle the uranium, we have another gain of, let's say, 10 or 15%. So we can reduce, for the same energy produced, we can reduce by 20 or 25% the consumption of uranium, natural uranium. But it will be very complicated to increase this uranium reduction in uranium economy saving with the same technology of the reactor. Sorry?
How expensive is it energetically to be recycled?
There is a lot of question about this. I would say that it is the difference of 2 large numbers. Large numbers have error bars. And so the result is 0 plus or minus something. But there is a lot of discussion. Is it economically good to do so? It's not sure. But I mean, the advantages are elsewhere. I can answer after. Okay, so again, to finish this part, the order of magnitude of 1 reactor for 1 gigawatt consumes 200 tons of uranium, 30 tons of fuel, 1 ton of fission. So the real energy use of the present reactors is around 0.5%. Okay, 1 ton divided by 200. It's completely normal because we use uranium-5. Uranium-5 is 0.7% of the natural uranium, so it's very close. Okay, and again, we can reduce by 25% these 200 tons, so we can reach perhaps 150 tons of natural uranium consumption per reactor per year if we do not change the technology of the reactor. So in terms of capacity to be deployed, considering this consumption of uranium, I made these 2 very simple scenario of nuclear demand in the future, factor 2 between today and 2050, and this famous factor 8 between today and 50 or 60. On the right, you see the cumulative uranium consumption in red, based on the consumption of 200 tons per year per reactor, and in red and in green, it's for a consumption about 150 tons, so 25% below. And this area here is the uranium resources we think we have. We can use, or we can we can use in the ground. Again, it's very difficult to have a good idea of the natural uranium resource. L'AIEA show every year the red uranium book, and the main value is always 16 millions of tons. Okay, some geologists say it's less. Some others say that it's a big. We can reach perhaps 20 or 30 millions of tons. I don't know, so I made hypothesis between 15 and 30 tons. So you see that if nuclear power does not increase the production significantly in the coming century, we should not have a problem about uranium resource during 100, perhaps 200 years. Of course, on the contrary, if the nuclear power is multiplied by 5 or 10 in the coming century, we should have a problem of natural uranium resource in the coming decade. When, I don't know, but perhaps. Okay, so, sorry. What happened next is this. Okay, so we know that we can use not only 0.5% of uranium, but 100% of the energy content of uranium. The principle is very simple. The idea is to use uranium-8, which is not a fissile material, but when the neutron is captured, we produce a plutonium-9, which is a fissile material. So the idea is to have a system, a reactor, containing uranium-8, a mix uranium-8 and plutonium, and you imagine that every time the plutonium fissions, it is produced again, it is bred by a neutron capture elsewhere in the reactor on uranium-8 to produce the plutonium which has disappeared. So this is a breeding principle. In this case, the plutonium is constant. So we have 1 ton of plutonium to produce 1 electrical gigawatt during 1 year. And 1 ton of plutonium disappeared and 1 ton of plutonium produced by uranium-8, neutron capture on uranium-8. So at the end, we have consumed only 1 ton of uranium-8 for the same energy production. So we divide by 200 the consumption of uranium to produce the same energy. Okay. So this is well known, but it's not so obvious to obtain this steady state of plutonium because now we have to calculate the number of neutrons which is produced by the fission and the number of neutrons we need to make not only the criticality of the system, 1 fission gives 1 fission, gives 1 fission, but also the breeding of the plutonium-238. So I just want to make this simple calculation. We consider 1 fission of plutonium. This fission produces new neutrons. For plutonium, it's around 2.9. It's a little bit better than uranium-5. So this is a neutron production. And we want, with these 2.9 neutrons, made 2 things. The first is to consume 1 neutrons to the chain reaction to maintain the fission in the reactors. And so we lose already 1 plutonium nucleus. The plutonium nucleus, when you see neutrons, it can make a fission, of course, but it can also capture the neutrons. So we have a parasitic capture of the neutrons. I call this alpha. It is just the number of neutrons captured on plutonium for 1 fission of plutonium. It is simply the ratio between the cross-section, capture and fission of the plutonium-239. So, which is important that we, for 1 fission, we lose not only 1 plutonium, but 1 plus alpha plutonium. So we have to breed 1 plus alpha plutonium again to maintain the mass of plutonium constant. So we have to consume again 1 plus alpha neutrons to be captured on uranium-8 to breed the plutonium. At the end, we produce new and we consume 2 times 1 plus alpha neutrons, and alpha is simply the ratio between the cross-section. So we can plot this factor here. It's completely calculated by the basic nuclear data, cross-section of plutonium-9. It is the black curve here. And you see, unfortunately, that in the region where the neutrons are in the present reactors, in the thermal part, low energy neutrons, we have a big resonance, which is not favorable because it favors the capture of on plutonium-238, and the neutron balance become negative in the PWR. So I mean, we cannot reach the breeding with the present reactors. We cannot make both criticality and plutonium constant in the reactor only with uranium-8 and plutonium-9. So we have to change the technology to reach the breeding. And you see that if we leave the neutrons at high energy, where they are produced by the fission, if we remove the moderator of the reactor, the neutron remains at high energy. And here we have a very positive neutron balance in the reactor. So it is why we consider fast breeder reactor, we need fast neutrons to breed the plutonium and to reach the breeding. And again, the breeding means two things: a system critical and only fed with uranium-8, and we completely forget the uranium-5, which does not play any role here. Okay. So it is a French. We already made this in the past. It is the French reactor Rhapsody Phoenix, Super Phoenix, which has been stopped in before 2000, and it was the goal of the Astrid project, which has been stopped a few years ago. There is I didn't mention that the main technology for fast reactor is the sodium fast reactor, because we have to find the coolant to transport the energy from the nuclear fuel to the turbine. And we cannot use water because water slows down the neutrons and so on. So we have to find a liquid or a gas. And it's not so easy. Sodium is very complicated to manipulate, but it is really the much more achieved technology to reach the breeding. The alternative are not so easy. Also, it's lead, and perhaps you know that we have a lot of problem of corrosion with lead at high temperature. Okay. So this technology should be completely sustainable in terms of uranium consumption. But we forget most of the time the question of plutonium, because I said that the plutonium is constant in the reactor, but we have to start the reactor. So we have to provide the reactor a quantity of plutonium to be started, and after, this quantity is kept constant by the breeding process. But we have to give this first inventory of plutonium. You can show again that the ratio of cross-section are sufficient to calculate this plutonium inventory, and I show here simplified calculation where we reach around 20 tons of plutonium to operate a 1 electrical gigawatt of the reactor. And I have to mention that the multi-recycling of the plutonium of the reactor is mandatory. We cannot avoid we cannot avoid the plutonium multi-recycling, because every 5 years we have to remove the fission product. We have to replace the uranium-8, which has disappeared, and the plutonium has to be kept. So he goes outside the core, it is treated, and he comes back in the reactor. So we have to multi-recycle and to close completely the fuel cycle. It is, again, mandatory. So 20 tons of plutonium for 1 electrical gigawatt. If you look at the French case, it's 60 gigawatt today. It's around 1,200 tons of plutonium. We have to dispose of this material to start the equivalent of the French fleet with breeder reactors the day perhaps we will need to reduce the uranium consumption. The situation, sorry, it's 2000 and je vais l'enlever. Voilà, situation today is that in the spent fuel, we have around 400 tons of plutonium, perhaps 430 tons of plutonium available, I mean civil plutonium. So you see that it's not so obvious to start a breeder fleet because we don't have enough plutonium to make the transition at constant power of the fleet today and the fast breeder in the future. So we have to accumulate the plutonium again and again to reach 1,200 tons of plutonium available in the spent fuel. So it is a very big question. And the status of the plutonium today is not a waste. It's simply a valuable material because we think that one day perhaps we will need it to start the fast reactors. Okay, so there is no ambiguity. If we think that we will need fast reactors, we have to keep the plutonium. We cannot consider it as a waste. We cannot burn it. We cannot store it in the ground. But of course, if nuclear power stops in France in the 20, 30 years, I don't know, the plutonium becomes automatically a waste. And in this case, it is a major waste. It dominates the radioactivity of the spent fuel, the radiotoxicity, the proliferation issue, the criticality risk during the storage, and so on. So the status of plutonium is completely dependent on the long-term hypothesis or the long-term strategy of France. A long-term means 50, 60, 70 years. And it's very interesting to see how we can manage this long-term strategy, which are very based on very basic, which are based on basic physics, I would say. Okay, so the status of French civil plutonium is valuable material, but it is more and more questioned today. The breeding paradox, just to finish, I have 5 minutes about the reactors at the end. Breeding paradox is another way to see the mass of plutonium is to say that 20 tons is roughly the plutonium which is produced by a PWR during its whole lifetime, during 60 years. 60 years time 300 tons per year, it's around 20 tons. So you can see here that we can make perhaps the transition between sustainable reactors only at constant power. So first, the breeding cannot ensure nuclear deployment. If I consider a factor 8, we will have to make a factor 8 with PWR, and we will have to consume all the uranium present on Earth or available, I would say. And then we will be able only to make the transition between a sustainable nuclear technology. So even if we don't use any uranium or very, very low uranium in the fast breeder reactor, they are completely dependent of the resource, and the resource we will be able to extract to operate the PWR, to produce the plutonium, to start the fast breeder reactor. I'm not sure to be very clear, but we can discuss about this during the question. I will finish very quickly by a very fast overview of the reactor technology, because we are talking about startup, about EPR, about molten salt. For me, it's very important to separate the different technology in two categories. The first is based on enriched uranium. There is no consideration of the fuel cycle on sustainability or the optimization of uranium consumption. The challenge here is to improve the safety, reduce the cost, and so on. And the second family, or the second categories, is very thought to operate the breeding and the fuel cycle. And it's very complicated for me to compare these two types of reactors because they are not conceived in the same way and the objectives are radically different. So all the projects we have today to produce electricity are based on enriched uranium. It's the EPR in France, AP 1000 in the US, CPR 1000 in China, VVER in Russia, and so on. It is the same reactors, water-cooled, uranium-enriched, and there is no consideration of fuel cycle and the consumption of uranium. And we have the same kind of reactor, but with a reduced power and a reduced size, which is called SMR, small modular reactor. For me, it's too early today to see to understand why or if this SMR will be competitive. But again, it works on the same principle that the big ones, enrich uranium, water cooled. Okay, but perhaps we can produce with these small reactors other things than electricity, perhaps industrial heat, hydrogen, desalination, and so on. But after that, we have some other reactors which are dedicated to producing high temperature heat. For example, the gas-cooled reactor or the solid fueled cooled by molten salt and so on. So there is a lot of different reactors dedicated to production heat. But here again, there is absolutely no consideration of the fuel cycle. And these fuels are so difficult to break, je sais pas comment dire. So we cannot imagine to recycle the fuel, the spent fuel of this kind of reactor. There is dedicated to heat production. And on the other side, we have the breeding reactors based on the super Phoenix or Phoenix technology, mainly sodium-cooled reactors, so the BN 800, 600 in Russia. For example, China has also started the construction of two fast reactors based on sodium, and we have some startup in France working on this technology, Otrera, Hexana, for example. The alternative is the lead. Again, there is one startup in France which is working on this. It is Nucléo. And at the end, these reactors, I think the objective is to operate the breeding and to make the nuclear power with fission sustainable. And just one word on molten salt, because we are speaking a lot about molten salt reactor, which is a very specific, very special reactor. The fuel is not solid anymore, but it is liquid. It is a salt. It contains the actinides, uranium, plutonium, thorium. I don't know. You can put everything in the liquid fuel. It is a very interesting reactor, I would say, on the paper, with attractive benefits. Again, we can imagine a lot of fuels. We can reprocess the fuel online because the fuel is liquid, so it circulates. So we can remove a small part of the fuel, treat it, and put it again in the reactor. And we can imagine passive evacuation of the power. Because the fuel is liquid, we can spread it in case of an accident and remove the residual heat very easily. Okay, so it is the theory. I say often that it is a dream of the physicist, but it is a nightmare of the chemist, because now when you see how you build such a reactor, it becomes very complex in terms of chemistry, in terms of materials, and we have to manage the liquid fuel circulating in the heat exchanger and so on. So, but again, we have some startup in France working on this kind of reactors. So I am too late. This is my conclusion, but I can stop here.
Thank you very much for this very enlightening talk. Is there any questions?
Yeah, thank you very much. That was very illuminating. I have just one simple question. You mentioned that we had this technology before 2000 for the fast breeding, recycling power plants, but you also said that we stopped them. Was there any good scientific or risk reason for doing that, for stopping those? What was the reason underlying that?
Okay, a personal answer. What I understand is that at the beginning of nuclear energy, at the beginning they thought that we should not have enough uranium to ensure a large nuclear energy production in the world. We were considered 2,000 reactors in 2000. It was the projection in the 80s. So between this and so we have started the fast breeder reactors from the beginning to very quickly replace the PWR. During that, we have a 3 Mile Island in the US. So the accident, we had completely stopped the nuclear deployment in the US. And we found a lot of uranium. So in the 90s, we had Super Phoenix in France, but we had a lot of uranium, not so much nuclear power in the world, so no problem of uranium resource during 20, 30 years. Okay. After that, you have the political situation in 1985, which has led to stop Super Phoenix. But it is a combination between political situation and the fact that there was no urgent strategy to use this technology. And it is the same today with Astrid. Astrid has been stopped because the view is to say we don't need to reduce uranium consumption drastically today. The price is low. The nuclear power grows relatively slowly in the world. So during 40, 50 years, there is no problem of uranium. So we stop Astrid, it is too early, and we prefer to start it later with a new system and so on. It's not completely stupid. It's complicated to, to make a decision.
Yes. Oh, yeah, so go ahead.
Thank you for the talk. Two small question. The annulation, cancelling of Phoenix or Super Phoenix, was it just for political reasons or also technical reasons? This is my first question. And second question is there any possibility to use lighter nuclei for as fuel? Is it
sorry, to use what fuel?
Lighter nuclei.
Lighter?
Yes, lighter what? For fission. Because
lighter nuclei as a lead or tungsten or so?
Yeah, yes, no. For instance.
No, yes. Because the fission barrier is too high. So when the neutrons hit the nuclei, it cannot. To fission a lead nuclei. Perhaps you have neutron. You should have neutrons of at least 20 MeV, and the fission produces neutrons at 2 MeV. So you cannot have a reaction chain. It works only with uranium, I would say. The first question I answered already. For me, it's a mix of political situation. It is a political decision, it's sure, in a context of where we did not need drastically to operate this kind of reactors. And it was complicated, I think, to operate Super Phoenix. It has been stopped during 2 years because there was a leak of sodium, and you know that sodium and water and sodium okay, it's not so good. So it has been stopped, but the year it has been decided to stop it, he worked, I remember, 97% of the time. So it was producing electricity a lot. The day that we have decided to stop it. And we had, I mentioned it, we had a reactor core, complete reactor core, ready to make the second cycle, because if we want to recycle the fuel, you have a reactor core, it operates 5 years, you remove it and you put a second one and you treat it. And we had a complete fresh reactor, uranium, plutonium, ready to be used. So we have lost a lot of money, I think. But
yeah, so thank you very much for the very interesting talk. Obviously, the big problem with I completely believe that we need nuclear power, so I don't want to come across as someone who thinks we shouldn't do nuclear power. The problem, of course, is the very high capital cost of the reactors.
yes,
I know that the small nuclear reactors, the idea was to mass produce them, but those kinds of reactors have become not so economically interesting because of the decrease in cost of renewable energy. You'll always need some baseline power. So given the current trajectory on the drop in cost of solar panels and things like that, how much installed base of nuclear energy would we need in order to meet the requirements of Paris, for instance?
difficult
don't need
question.
to build
How much
you don't
nuclear in the
Yeah.
electricity mix, for example, you mean? It's complicated. It's not my specialty, I would say. Perhaps 50, 75%, as we have in France, is perhaps not the optimal. It is perhaps 60, 50, I don't know. When we see the RTE analysis, it stops at 50% of nuclear, between 0 and 50. And at 50, it's the best in terms of cost, global cost of the system, meaning renewable storage, nuclear, and so on. So I would say that the optimal is between 50 and 60. But
maybe building nuclear reactors would be more interesting if there was a carbon tax.
yes, of course.
Yeah. Because the cost is not figured into
But it's also difficult to discuss the cost of the price of small reactors compared to the big ones. The doctrine, je ne sais pas comment on dit en anglais, the main line during 50 years is the biggest, the lowest cost. Okay.
But they're all one-off reactors. They all have different designs, more or less, do they?
Sorry?
Each reactor has a different design and is more or less a one-off in each site. That's why they take so long to build, is it?
Yes, but the idea that small reactor could be cheaper, more easy to construct, and so on, it's a new idea. And I don't know how it has been, it has started.
Microsoft.
And we don't have the result today. And
Microsoft were funding a reactor startup, which they stopped
you can
because
say
it was no longer interesting.
To have a private fund and so on, it's perhaps more easy with small reactors.
Yeah, you were talking only about fission. You can understand that we astrophysicists are perhaps more interested in fusion, which is happening in the stars. So I understand from at the very beginning, you were quite skeptical about the future of fusion to produce electricity. Now we have ITER in the south of France. And I think last week they announced in the US for the first time they had a positive outcome for a fraction of a second. So what is your feeling about the long-term perspective in fusion? Maybe it's a completely other talk, but at least to have an idea of the perspective.
The positive energy ratio, I understood that they didn't take into account the efficiency of the laser. So the electricity consumed, the ratio remains much below 1, I think. But I cannot answer. I don't know. I just say that it will be a little bit risky to make a bet about fusion energy when we see the difficulty of ITER. ITER will start in 2040 and will give the first perhaps results of it is possible or not, as compared to fission reactors. We know it's possible. There is a lot of technological problem and so on, but all the physics principles are known. So, well, okay. No, I don't want to answer about fusion. I don't have skill on this. No, what I could say, if it works, it's not so bad because we don't have high-level waste. It's true. We only have activation waste by neutrons in the walls and so on, and we don't have residual power. You know that in the fission reactors, the fact that we produce fission fragments which are radioactive with period of a few days, a few weeks, it means that we have to cool down the reactor after after stopping the chain reaction. And this is the major safety issue of reactor. It happens to Fukushima. Fukushima, the reactor has stopped, but after the tsunami has destroyed the capacity to remove the heat, the residual heat. So there is no this kind of problems in the fusion. So it is very interesting. Yes, the problem is, okay, so no residual heat, no high-level waste. So if it works, it should be good. But we have exactly the same, the same constraint on the fuel, because the fuel of the ITER project is deuterium tritium. Tritium is not present in nature because the period is 12 years. So we have to produce tritium with lithium 7 plus neutron, I would say, or lithium 6, I'm not sure. But so the fuel, the real fuel is lithium. And we produce neutron. And we produce only 1 neutrons, but we have to breed 1 tritium and more than 1 tritium because we have a loss of tritium during the process. So we have to multiply the neutrons and to breed the tritium with the reaction on lithium. So we have exactly the same neutron balance, uranium 8 plutonium, and the lithium and the tritium. It's interesting.
So I have a question regarding when Superphénix stopped. I remember from those days that there were a lot of demonstrations also from green parties about the leaks of sodium. Was that justified risk? Is it still justified as an argument against those fast neutron reactors, or is it completely mastered now?
I would say it's a technological difficulty to use sodium. And present innovative sodium reactors try to avoid any heat exchanger between sodium and water. But it was made in Superphénix, if I make no mistake. So we can imagine sodium, molten salt, and molten salt water, so, for example. So they are working on this. But it is a problem of sodium.
Very last question.
Hi, do you think the research in the field of nuclear physics is heavily influenced by the political landscape of the country? And if so, like
if it is influenced by political
landscape of the country, and if so, like could this be a barrier for like people to like come and work into the field of nuclear physics?
Okay, I'm not sure to understand the question. Is the
Do people do nuclear power to make bombs?
for me today, it's not. There is a separation between the. Non, je suis pas sûr d'avoir compris la question. Non, c'est intéressant. Is there a political power to on the research, on the innovative system?
Like does politics have a lot of influence on the research in nuclear physics? That's the question.
Yes, I would say yes. During 15 years in France, I think that we had a political position very no pro-nuclear. I don't say anti, but no pro-nuclear.
It's not just in France, right? It's across the world.
Across the world. Difficult to answer. I don't know. We can discuss about that later.
Well, thank you very much. There were a lot of questions, a lot of interest also online. But thanks again.
Merci. Ah oui.